All right, so we've done a lot already this term with techniques for solving first order differential equations. We looked at some applications of those. So there's a couple of other things we want to accomplish, and the next one of those is linear second order equations. And again, this is being recorded, of course, during the lockdown with the coronavirus, so I apologize that you're in my in our playroom actually at home, and I'm unable to post some good homework like I've been doing, so it'll be a handwritten document, unfortunately, probably at the end of this. So just know that, and be sure you're getting to your homework on these as well, okay? But remember, from the very beginning of the term, a second order differential equation is one where I have a y double prime. So we've solved things with a y prime in it, first derivative. Now I'm looking at things with second derivatives. But I'll be honest with you, y'all, the work here is nothing. At least for the first half of it, the work is real easy. And even with our first technique, it's relatively easy to solve. So most of the difficult stuff is behind us. And so I'm glancing at a textbook as well because I don't have all my materials at home. So we want to begin by solving this type of equation. And when it's equal to 0, and we've used this word before, I think, but when it's equal to 0, we generally call that the homogeneous solution. And I'll go ahead and tell you, we're going to talk eventually about some other ways to solve these, but we're always going to find this homogeneous solution. So even if it's got some other stuff in here equal to something else besides 0, I'm still going to set it equal to 0 and solve that first. So just kind of keep that in mind. So just glancing at this, you know, if you have ever taught algebra or remember some algebra from high school, when I look at that equation, immediately my mind goes to a quadratic equation. That's just what that form looks like, and that's absolutely going to lead us into our technique for solving those. So I want to look at some examples with you. And again, we're going to make all of these things into, essentially, to start with anyway, quadratic equations. All right, so keep in mind, I'm looking for a function y whose derivative and second derivative satisfies this equation. That's what we're on the lookout for. And so the first thing I'm going to do, and I'm going to write this down right now, but probably not again, we're going to find what's known as the characteristic equation. I want an equation that kind of sort of resembles this equation. And again, I want it to be a quadratic. So everywhere I have a y or y prime or y double prime, I'm going to replace those with r's. Oh, and I've already messed up. So this is the equation that I want to solve. R squared plus 5r plus 6 all equal to 0. And so we're going to use our favorite techniques for solving those. You can use the quadratic formula. You can complete the square. I can look at this, and you can too, and know that this just immediately factors. And so I get solutions for R of -2 and -3. Now, again, these are leading me to this characteristic equation. So let's go back and think about what that looks like in terms of a solution. So I want to build a solution based on these two things. And the solution's always going to work like these as far as this type of second order equation. So I'm going to call this y sub c, and so this represents the solution that we've gleaned from the characteristic equation, right? Right now, that's the only thing that I've got is this characteristic equation, this homogeneous case. So this is going to be the solution. But later on with this material, we're going to have both a characteristic piece and what we call a particular solution, and those two things put together are actually going to be our solution for y. And so these are always going to come in this form, at least for roots of that nature. So some constant that I don't know of times e to the -2. think I generally use t's here, but if I suddenly start using x's, don't let that bother you. It's just a variable. So this just says some constant that I don't know, but I could find if I'm given some initial conditions like we've done, e to the negative 2t plus some other constant, e to the negative 3t. This is actually the solution set to this problem. And yes, it's that easy. These are not bad problems at all. Okay? So number 2, let's look at a similar one to that, and then we want to think about what all potentially could happen with quadratics. Maybe I'm looking because I want to assign some of these for you. So maybe this y double prime minus y prime minus 2y all equal to 0. Oh, by the way, if I take the derivatives here and substitute them back in, you know, we could do that and convince ourselves that it's actually a solution. I'm not going to do that. So my characteristic equation looks like this: r squared minus r minus 2. Again, I believe that factors. Just as a side note, I'm kind of glossing over the factoring, and I'm going to continue to do that. I think you all are comfortable with factoring, but if you're not, then we need to find some resources to help you do that. And if I happen to have a mistake after this recording, you know, that happens. By all means, call it to my attention. But I'm getting roots here of 2 and negative 1. So my solution then is c1 e to the 2t plus some c2 e to the negative 1t. And I think you know this, but perhaps it's worth mentioning. If you use the negative 1 first and then the 2, you know, by the commutative property, we have similar solutions. We've talked before about these c's and just they're any constant. I don't know if this c is the same as this c, or if you have yours swapped. If you know, you understand what I'm saying with that. The c's are arbitrary, so they can be anything. All right, so that's as easy as that is. So what all could happen then when I go to try to factor a quadratics? So I've looked at the most common case, or the case we like the most, where I have 2 distinct roots. But other things can happen with that as well, right? So 2 distinct roots, that's how I'm going to do the solution. And let me just write that in there. 2 distinct roots. But think about the other things that could happen with that. I could get a repeating root. That's not that uncommon. And I could get some imaginary roots. And so that's the solution kind of changes based on the problem itself. So let's look at each of those other cases. Example 3, I'll call it. Let's do y double prime minus 4y prime plus 4 all equal to 0. So again, that characteristic equation looks like this, and it factors. By the way, we could certainly use the quadratic formula if you can't get it to factor, but there it is, factored. But I don't get a distinct root this time. I actually get a repeating root. So I just need to address that. I want this solution set, this y sub c portion, and I don't want to go into a whole lot of theory here, but it's worth mentioning. I want these things to be a linear combination, and I want them to be produce for me 2 different possible roots there, 2 different pieces of the solution. And so when we have a repeater, we just force that to happen. So my first solution is e to the 2t, and then that second solution I'm going to modify, and so this is the modified second solution, and that's just going to be the case every single time. Oh, I'm sorry, my bad, e to the 2t. I'm sorry about that. E to the 2t in both, but the second one gets modified by the addition of this extra little t times e to the 2t in there. Okay, so 2 distinct roots, both of them are what they are. A modified root, if we have a repeater, then we have to modify it and we get a root like that. Okay, so let me find this one. I won't work another example with that, although let me look at just before we talk about the imaginary case. Look at this solution, or this equation with me. Y triple prime minus 6y double prime minus y prime plus 6y all equal to 0. And so even though it's an even higher order equation, it's a third derivative, this technique is going to lend itself to this situation. So if I write that characteristic equation, r cubed minus 6r squared minus r plus 6 equal to 0. Sorry about my typo there. So how do we solve something like this? Well, if you've taken college algebra, and you all, I'm sure, have, I always tell my algebra students, whenever we see 4 terms, the first thing that needs to come to our mind is factor by grouping. We absolutely could use synthetic division and all of those other techniques, the rational root theorem and all that kind of stuff, but these aren't going to be that involved, maybe. So when I see 4 terms, immediately I think grouping, and I look for something in common with the group. And then this is always the tricky case students talk about, right? So our r squared in common with the first 2. And in order for this to work, and you know this, in order for this to work, this parentheses and whatever I get in this parentheses has to be the same. So keep that in mind. And it looks like there's nothing in common here, but I can always take out a 1. That's not going to work for me here because I'm not going to get the same parentheses. What I want to factor out is a -1. So let me just kind of recap all of that. If I distribute -1 times this parentheses, I get this piece back. So I haven't done anything wrong. Furthermore, this stuff factors, right? Or now it's the same and is factorable. So to do that, what I'm going to do is to always tell students, and again, y'all know this, you graduate students, I can take out, treat that as 2 terms and take out an r minus 6. And so I'm left with r minus 6 times r squared minus 1, which also factors into r minus 1, r plus 1. So I get possibilities for this triple derivative problem, at least for the characteristic equation that looks like this. So my solution set here is e to the 6t plus some other constant e to the 1t plus a third constant e to the -1t. So again, the rules haven't changed. If we end up with a repeater, we address that repeater as well. Okay. So the last case is when I have a complex root. And so with complex numbers, I'm going to use the quadratic formula. Maybe, you know, sometimes I can do it without using the quadratic formula, but to begin with, the quadratic formula is going to be important. So when I solve the quadratic formula, and again, we can get into a lot of trigonometry and ideas here with complex analysis, but my solutions, and I've used X here, and I think my problems are going to be T problems. So again, don't let that throw you off. I use different notations in different classes depending on the textbook. It's all the same stuff. But with a complex answer, I get something of this form, where alpha and beta are just numbers. Okay, so alpha is what we call the real part, and beta is what we call the imaginary part, which really, in the big scheme of things, is neither here nor there for us. We're going to use that to produce a solution that fits this form. E to the alpha t cosine of beta t. Let me be sure this textbook is using cosine first. I want to be sure that was the case. And some other constant e to the alpha t sine beta t. And I don't know if you've done any complex analysis, and this is absolutely not a complex analysis class, but just quickly, if I think about this as the x-axis as corresponding with the real part and the y-axis is corresponding with the imaginary part, then essentially if I plot some real and some imaginary piece, what I end up getting is a right triangle with some alpha distance here. Let me change this to the real axis so I don't let the variables confuse you in the imaginary axis. And sorry, alpha here and beta here. There we go. I think that's finally right. And so essentially my imaginary number with these two pieces can be represented as a trig function is what that's doing, where and again we do this all the time in trig, where the x distance here, the alpha, let me do it this way, the cosine of theta is equal to well, I'm getting into too much trig, but anyway, you can remember that the x-axis corresponds with cosine typically. If you think about the unit circle even, there's lots of places that, and I'm talking about this more than I ever wanted to, so, but likewise the y-axis deals with the sine value. If you happen to flip-flop those, it's not the end of the world, again, by the commutative property. So let me find this one that's got an imaginary root. Yeah, let's do number 5. Let's do y double prime plus 9y all equal to 0. And so if I write the characteristic equation for that, that's going to be r squared plus 9 equal to 0, or r squared is equal to negative 9. And again, you can do the Pythagorean theorem. Sometimes I'm sorry, the quadratic formula. Sometimes I have to do that. But I think we can agree that if I take the square root of either side here, then I get just plus or minus 3i. So again, if I'm making that fit that form, then essentially I have no real piece for this particular problem, and that's okay. It'll come out in the wash. So here we go. The characteristic equation solution is going to be some constant e to the 0t cosine of beta t plus some other constant e to the 0t times the sine of beta t. And you already know that 0 times t is 0, and e to the 0 is nothing more than 1. So my solution to this particular problem looks like this. And again, that wouldn't be a bad one for us to take the derivatives of and to substitute back into the equation. And you can kind of see that as I differentiate sine and cosine, I get positives and negatives out of that. So they'll end up, when I plug them into this equation over here, they'll end up officially, canceling themselves out. I'll leave that for you to play around with. Let me find us one where we get maybe a real piece with it. Let's try this one, number 6. This textbook says W double prime, and I'll do that just to keep us honest, plus 4W prime plus 6W all equal to 0. And so the characteristic equation looks like r squared plus 4r plus 6. And again, I'm not seeing any way that that is factorable. So let me plug it into my quadratic formula. Opposite b plus or minus the square root of b squared minus 4ac all over 2a. Maybe it'll sort of kind of simplify. That's going to be 16 minus what? 24. And 16 minus 24 is negative 8. And I can simplify negative 8 just a tiny bit. Negative 8 is the same as 4 times negative 2. And 4 is 2. the square root. And I can take care of the negative. I'm not sure why I didn't do that then. But negative 4 plus or minus 2i square root of 2 all over 2. And then finally, I can divide this 2 everywhere. So again, this is now my alpha, and my beta is square root of 2. So my solution set for this problem looks like, it's actually a W function now, isn't it? Some C1e to the negative 2t, cosine of square root 2t, plus, and I'm going to go off your screen, so plus some second constant, e to the negative 2t sine of square root 2 times t. So again, these problems are not bad at all. Most students like these. They're relatively straightforward. You just have to remember each of the three cases, a repeating root, two distinct real roots, a repeating root, and then the imaginary case. And again, we're going to find these every single time for everything that we do.